The challenging times faced by business these days have shown the difficulty in managing HR issues and maintaining profitability. Keeping focus on the core business and finding the right partners to help with ancillary functions like HR administration is why more than 500 companies across the country turn to Tryon Solutions. Tryon relieves the stress and burden of HR administration so companies, small to large, can stay focused on why they went into business in the first place. Small companies turn to Tryon to manage their payroll and taxes, benefits administration, workers' compensation, and regulatory compliance, so they don't need to build a big HR department. Larger companies add Tryon as an extension of their existing HR staffs, achieving efficiencies and enhancing the bottom line. Check out Tryon at RelyOnTryon.com and receive a free consultation from one of its business advisors. It'll be the best business decision you'll ever make.
Hey, Campuseros, welcome to Reboot the World Campus Party's first ever digital edition. We are so excited this evening to have Invensity with us today. Representing them, we have Josh, Tejasvir, and James. They are going to speak on where are those self-driving cars. Take it away, gentlemen.
She said, I'm Josh.
I'm Tejas.
And I'm James.
And we're going to tell you where those self-driving cars are. So just a quick overview here. We're going to first talk about why we don't have them on the road today. What are the issues, the immediate issues there? And then we're going to go to what do we have in place today that we're currently using to make that actually happen. Then we're going to talk about what's next. How do we get to that next leap? And then we're going to conclude with why those things that we present to you are going to solve the challenges that we face with self-driving cars today. So why don't we have autonomous vehicles on the road today? So the main thing is we must ensure that all vehicles, whether they are autonomous, electric, diesel, internal combustion, hybrid, any combination of vehicle, they have to be safe, whether that's in crash tests, whether that's in cybersecurity, and now more and more commonly in advanced driver assistance systems, ADAS, or self-driving cars. So it makes business sense for these companies to make safe cars because, as you can see on the right here, that is the number one. Car safety is the number one figure when customers are looking to buy new cars. So then the safer the car, in theory, the more appealing it would be to customers, especially when it's a new technology such as autonomous vehicles. Because if we look at history, in the case of the Ford Pinto, the Toyota Prius accelerating randomly in the Takata airbags, building up trust with the customers after the fact of these accidents is very difficult to do. So we first need to understand what are we defining? What is safety? What is risk? What are these terms that we're talking about so that we can know if we're meeting them or not? So start right off, who's we, right? Who is going to be saying what the safety is? Who's going to be agreeing if it's safe or not? So we, in the context of this presentation, is going to be the manufacturers themselves, whether they're OEMs, suppliers, and government regulating bodies. So who is defining? We have to take into account, is it just the engineers that are defining who we is, what safety is, or are they sourcing information from other stakeholders? So what is safety, right? Safety is the absence of unreasonable risk. And so by that definition, there is kind of openness that you will not be able to eliminate every single instance of an accident, and you won't be able to 100% have a safe system. So keep that in mind. So what is risk? Risk is a combination of the probability of occurrence of harm and severity of that harm. So risk is something that's to be factored in, and risk, as you can see in the graph, is a combination of the probability and the severity. So as the severity increases, the probability has to be taken into account for likewise. A hazard, potential source of harm caused by malfunctioning behavior of the item. And all these and more definitions, such as what is acceptable, what is an acceptable level of risk, is 1 in 10 acceptable for a camera to not detect a passenger? Is it 1 in a million? Is it 1 in 10 million? These are all things that need to be factored into when you're defining how safe you want your system to be. And so now that we agree that everybody needs to define them properly, we need to make sure that everyone is across the board using the same definitions. If BMW, General Motors, and Honda, for example, are selling a car in Europe, they probably are also going to be selling that car in the United States and need to match accordingly with those governing bodies so that a car that must be safe in 1 in 10 million scenarios will meet the 1 in 25 million scenarios in another entity. So with that, I will hand it off to James to discuss what we have in place today for safety in automotive systems.
Hey, thanks, Josh. So we know that we need some kind of a standard to help bring our terms together, to help bring our processes together in order to ensure that the systems, the vehicles that we're putting on the roadways for real people like you and I to drive are safe, right? So we can talk a little bit about, and what I want to share with you guys in the next couple of minutes is what we're doing right now. What do we have in the current ecosystem that we're utilizing to develop better systems that are really going to be safe on the road, that aren't going to be causing a lot of death or mass paranoia and things like that. Now, it's important as I go through these next couple of things, there are two things I want to talk about. One is what does this standard cover? And the standard that we're going to be talking about is ISO 26262. And I'm not going to go into a tremendous amount of detail. I just want to give you a high-level overview so that you can kind of have an idea of what's actually happening. And then the second thing is, how does it actually help us today? Because it's not enough to have the tools. You have to know how to use them, and you have to know what their strengths and weaknesses are. So all of that is going to be in the context of the fact that this will apply to the kinds of vehicles that we see on the roadway today, i.e. Electrified vehicles, systems or vehicles with embedded systems and things like that, driving them, not so much autonomous vehicles or things like that. This is maybe a preliminary step, but we'll get to that in a little bit more detail in the future of this presentation. So right off the bat, there are a number of methods that have been used for a long time by various parties to improve system development to address this safety concern. Things like a fault tree analysis, which is really taking a hazard, which is something that we don't want to happen in the system or in the environment, and tracing it down to the individual faults that in the system that could be causing that hazard to occur. An FMEA, which is sort of the inverse of that, and this is one that I actually learned in school, so it's certainly been around and is well regarded for a long time. And an FMEA, a failure modes and effects analysis, is really looking at the system in detail and trying to find everything that could go wrong, and then speculating and saying, okay, well, if this fault happens, then what actually occurs on the system level, on the functional level in the vehicle, and does that violate our safety goals or the hazards that we've set out to try and avoid? Then there are a number of other tools. So this is just a handful of the analysis tools. There's a dependent failure analysis, which kind of addresses the weaknesses of those analyses. There's a hazard analysis and risk assessment, which really focuses on how do you identify what those hazards are for your vehicle, and how do you associate the level of risk that you have, and we assign something called an automotive safety integrity level to that. And then you have testing and things like this. But the point is that there are a lot of tools that have been developed for a long time. And what this standard does, ISO 26262, is it actually brings all these things together into a process framework that is usable and helps guide organizations to be able to implement them in an effective way where their strengths and weaknesses are already considered. And as long as you follow the processes, then you don't have to worry so much about the details of making sure that you covered every option in your own development process. So, and part of the reason that this is important is because of the world that we find ourselves in today. I think if we look around at vehicles that are made in 2020, and we compare those to vehicles that are made in 1996 or the early 2000s, what we'll notice is that the complexity is a step higher. And we might experience that as in vehicles are more comfortable, or they have more features, or they do this fancy braking thing when I forget to brake for the car in front of me. And all of that is true, but it also means that to implement all of these things at a higher level and in a safer way, it becomes harder because it's more and more complex. There's more going on. At the same time, a lot more things are controlled by the vehicle itself. Things like automatic emergency braking that decides when there's something in front of you that the driver has missed and decides how hard to brake and when to brake. That's something that we didn't have in most vehicles 15, 20 years ago that we now have to consider. And that introduces more faults. Where in the past, all of the faults were simply mechanical, right? If you could pick any part on your car, and if it fails because it breaks or it overheats or whatever the problem is, that's relatively simple to diagnose and to understand because you look at it and you can replace the part and it'll be good as new. And so then you would have built-in redundancy for that and all these sorts of things. But in current vehicles, you also have to consider the faults that could come from things like your electronic control unit, right? If you have an ECU that overheats and all of a sudden it can't actually perform the functions that it was designed to perform, how is your vehicle going to handle that situation? Because it's a lot more difficult and a lot more dangerous when the vehicle is making those decisions for itself. So this standard takes all of these things into account and actually creates a process framework for the entirety of the system or of the safety lifecycle process. And so that's what you can see on the screen here. And the idea is it doesn't just look at the system development phase, and more importantly, it doesn't just look at the hardware and the software. It starts, the functional safety has to start and run in accordance with the system development process implemented by the organization. And it starts all the way up at when you define what you want your product to do. And so it starts with these things called item definitions and hazard analysis and risk assessment, which is all about sifting out what are these top level requirements that we call safety goals, which is basically what's happening in the system, or what could happen in the system, or more to the point, what do we want to avoid? Safety goals are driven by those hazards that we've talked about before. And then we go through and we take that and you can turn it into functional safety requirements, and then eventually technical safety requirements. And the idea is that each level down you go, they become more and more specific to the real implementation. Eventually you end up with software safety requirements and hardware safety requirements, which are the real way that they're implemented into the design of your system. And so it's really important that you follow all of those steps and that we treat functional safety as integral into the product development. Because if you try and skip those steps and you start with, okay, well, I know what I want my car to do, and you skip the step of, okay, but how do you ensure that that's happening? Then what happens is you have software requirements and hardware requirements that are specifying some behavior in the vehicle, but that doesn't actually accomplish what the goal of the functional requirements were. And so that's sort of the left half of this model. If you guys haven't seen this before, this is what's commonly referred to as the V model. It's just a typical systems engineering model that's used a lot in industry because it's simple, easy to understand, and talks about the whole life cycle. So the left half we talked about, that's all covered by functional safety. Those tools that I was talking about on the first slide of this section were, they fit in here, right? Under the system analyses, you can put your FMEA and your DFA and things like that. Under the quantitative measures, and also there's another section that goes in there, there are tools like a software event tree analysis, which is very similar to the fault tree analysis, except it recognizes that software doesn't fail. It might make mistakes because there's logical errors, but it can't fail. So there are a lot of different tools that are talked about in the standard that cover the left side of the development. But if you guys have ever made anything, one thing I think you'll know is that you don't know if it works until you test it, right? It's really easy to type up some program and and you think it's going to work because you thought through all the steps and what you're writing, and you're really confident, and you run it and you find some bug. Well, that's sort of the whole right-hand side of this V, and there's a lot of details and specifications around how to do the testing and the verification for these systems in a way that is clear and ensures that these safety elements on the left side were considered. And so that is really what the standard talks about. And it's, like I said, it goes into a lot of detail. It's quite a long document. It's a ton of fun to read, let me tell you. But the important thing to understand is that when it's implemented as a regular part of the product development, then it will ensure that the types of vehicles that we see on the road right now are safe. But it does have some limitations when we get to vehicles that are really fully autonomous, where the primary set of decisions that are being made by the driver in the vehicle are actually happening from the vehicle and not from the driver. It's a lot more likely that you're going to run into mistakes, and that's why we need this next thing that's in the future.
Thanks, James. So now the question comes, what's next? James gave you a little bit of an overview on how ISO 262 covers a bunch of technical failures, systematic failures, electronic failures, your automatic emergency braking brakes by itself, your steering wheel turns by itself. These are all things that can be tested, can be figured out. And in our current sense, specifically with ADAS, with ADAS systems, that's something we can do. ISO 262 can definitely help. Now, our topic was, where are those self-driving cars, right? We love to see the Jetsons, and we dream about this whole futuristic vision of a car being able to just take us from our home to our office to work, back to a baseball game and back home. But how do we actually envision that? The ADAS system kind of supports our driving, but how do we actually get the fully self-driving car? And if we're going to do a fully self-driving car, that means there's probably going to be a little bit more issues. So that's where SOTIF comes into play. And when I say SOTIF, that stands for safety of the intended functionality. So the use of algorithms, use of AI for driving functions brings up a lot of situational risks that are actually not covered by ISO 26262. So although ISO is very important and having functional safety is important, it covers it to a certain level. And then there's this whole realm of algorithms and automated, just a machine inside your system being able to try to think for yourself. And this AI whole concept is where things get a little bit confusing. Now, everyone talks about, okay, if the self-driving car is going in and at an intersection and it sees a dog, or it sees a dog and a person, what does it do? If it sees an animal and a biker, what does it do? There's a level of decision making that needs to take place. But there's a little bit more specific scenarios that we think are a little bit more relevant, specifically for our situations, specific to self-driving. So automated systems have huge volumes of data. This data is fed in by complex algorithms, and to avoid these safety hazards, AI makes the decisions. So ISO does try to aim and identify and reduce the number of unsafe scenarios, but there is likely going to be where AI is going to have to make certain decisions, and in order to do that, it's going to have to reduce these certain kind of hazards. So there's a different kind of coverage that ISO needs to that SOTIF provides that ISO 26262 generally does not. And the goal is to give guidance on situational scenarios that can be covered, that cannot be covered by a systematic failure. So once more time, just to repeat myself, ISO 262 focus on systematic failures, which is very, very important, right? If you have a lane keeping assist and you're sitting in your car and you think your vehicle is going to do that and keep you in the lane for the next 30 miles, but all of a sudden it decides to change lanes. That's a systematic failure that occurs due to something in your system going wrong. That's a systematic failure. But situational scenarios where the vehicle is actually operating as it should, but something happens on the external part of the vehicle, that's where SOTIF comes into play. So if you take a look at this graph, it's a little bit complex and it's a little bit confusing to understand. But what I try to explain whenever we go over this is that the dark green bubble, 1, that's the known safe scenarios, whereas 3 is the unknown but safe scenarios. We are trying to minimize X and 2, and considered the unknown unsafe scenarios, and the 2 is considered as the known unsafe scenarios. What we want to do is minimize that unknown, but also unsafe scenarios. And what do I mean by that? So let me give you an example so this kind of comes into perspective. In Germany, apparently, there are vehicles, and we were talking with one of our colleagues, Sasha. He was telling us about they have paintings on the roads, which kind of help in deciphering, if there's a children's crossing, similar to in the USA, we have signs, but they'll have drawings on the roads. Now, if the vehicle with automatic emergency braking and it has connected to an optical camera sensor is driving, and there's a very lifelike painting resembling a child playing on the driver to raise awareness. If this image on the road comes into play, it could hypothetically trick the optical vision system. It could actually lead to maybe false pedestrian recognition. Your camera system might classify that as an actual human being. It might classify the ball as an object and slam on its automatic emergency brake. So the vehicle is performing as it should. The vehicle looks at the road, figures out that, okay, I think there's something there, and makes an effort to stop the vehicle. But it's performing exactly as it should, but in the grand scheme of things, it's still a hazard, right? If you slam your brakes unknowingly in the middle of the road, it could cause it to rear-end collision, it could cause yourself to get some kind of an accident, it could lead to a multitude of things, depending on what speed you're going. So what SOTIF does, it says, hey, let's analyze this in a different way. Let's analyze this in a little bit more realistic way. If your camera vision recognizes something, maybe you need to double check them with additional sensors. Maybe you need to improve your recognition algorithms. These are all different small topics that SOTIF can help improve. If you take another example, a much more simpler example. In Michigan here, it gets very snowy. It ices over, we're driving, and we realize it's dangerous. A self-driving car may not recognize that, certain things we just, as a normal human being, when we get to a stop sign, we'll slow down a little bit more hesitantly and a little bit more carefully rather than how we would slow down when it's in the summer. But as a self-driving car, you make decisions just on the base of your scenarios. So if it tries to slam on the brakes at a more aggressive rate, we can cause some slippage, we could cause the vehicle to cross over to the intersection, cause an accident. These are all different scenarios where the vehicle is operating as it should, but it needs to be aware of its environment, and it needs to make sure it prevents any hazards in that scenario. So let's compare and contrast. So ISO 262, that's what James and Josh talked about. There's SOTIF on the other hand. I'm not saying that we need to do one or the other. We actually are trying to say that there's a combination of these methods that need to come into play if we really want these self-driving cars onto the road. So ISO covers systematic failures, electronics, hardware. SOTIF covers situational and environmental scenarios. There's the whole V model that we talked about at ISO 26262. With SOTIF, we made up this term. It's called a W model, and I'll get to that right after. The analysis for functional safety in ISO 262 happens at the beginning or during the product development. So, as the product is being developed, you're working on certain things and actually getting this product up to speed and working on making it safer. But SOTIF actually comes before ISO actually starts. And if you work on this process properly, the information and the knowledge you get from SOTIF can in turn also help your functional safety process. Just to give a little bit more information to those people who understand how the V model works, we're talking about doing things that kind of iterate each other. So there's the HARA that James talked about, hazard analysis risk assessment. SOTIF also has a specific HARA that we work on, but these scenarios are very different. But if an engineer who's working on a SOTIF and SOTIF HARA and an engineer who's working on the functional safety HARA start talking to each other, they'll be able to come up with more ideas. They'll come up with more scenarios. They'll come up with, hey, the SOTIF engineer can say, I found some things that actually apply to you. Whereas the functional safety engineer says, hey, I can find things that apply to you. And this process is iterative. So you can actually improve exactly, you can improve your SOTIF standard, you can also improve your functional safety, but the big thing is you end up improving your entire product cycle. So a combination of this, right? ISO 26262, we're talking about systematic failures. SOTIF is the scenario, the environment, everything in your surrounding, but actually performing as it should be. The vehicle performs as it should be, but the scenario and the environment may cause different hazards. Combining these two different analyses may actually lead to releasing the self-driving vehicle. But before we jump into that, let's have Josh come back and give why this helps solve the challenges that we are in the world today.
Right. Thanks, Tejas. So definitely sounds like each one of those functional safety and SOTIF take quite a bit of time. So why does this solve the challenges in the world today, both SOTIF and functional safety? So I think it's safe to everyone can agree that insufficient technology simply can't be the reason why we don't have self-driving cars today, right? We have robust cloud infrastructure to relay large volumes of information between the cars themselves, fleets of cars, the simulations and things like that. So it can't be that. Processing power isn't a limiting factor. Cars have had 1 kilowatt power supplies in the back of them, and probably now even bigger than that. It can't be the connectivity between the users themselves and the vehicles themselves. There's more and more wireless coverage to allow the sharing of information. There's just so many more technological advances every year that make it easier and easier for us to reach this technological hurdle. But so what is the real reason why big companies like Tesla, Uber, Google, even the DARPA self-driving challenge from years ago that initially sparked the self-driving challenge, why have none of them been able to crack this code? So as you can see right here, functional safety and SOTIF currently only go up to level 2. Autonomy is defined by SAE, the Society of Automotive Engineers. So ISO 26262 is necessary for all level 0 vehicles. So that is, think of the first car you had, the first car your parents had, cars like that. Nothing fancy, they just get you from A to B. Maybe if you're lucky, you had power windows. And so that still applies for all the way up to level 5 cars. So as Tejas said, once you wanted to start moving up into more and more advanced cars, that's where SOTIF comes into play at level 1 all the way through level 2. And that is just the bare minimum needed for level 0, 1, and 2 vehicles. So then we get into level 3, 4, and 5. What the heck? Why don't they work? What's not covered? And that bleeds into the next level of things that are out there. There's a standard out there called UL 4600 that is seeming to be the next governing standard. There is a cybersecurity standard that is currently in use, and as cars get more and more complicated, more connectivity and things like that, we no longer can just kind of get by on siloed approaches to engineering. So the real reason why we don't have self-driving cars on the road today is simply because the safety process and maturity is not nowhere near what we need for a level 4 or 5, where you can just, as Tejas said, get dropped off at work, get picked up, go to the baseball game, come home, and you don't have to touch the wheel. You just tell where you want to go and when you want to go. And that presents an interesting situation for all these companies that are working on these self-driving cars. And that is that nobody wants to risk being first, because whoever's first sets the baseline for safety, so the next person can just easily one-up you. And then you also could be held more liable for when things go wrong, because you were the first to say, hey, it's level 5, it's safe. Watch Harry Potter on Netflix on your the big infotainment screen you have there, and that's it, you're done. But we are still so far away from seeing those safety processes being implemented, because we are only seeing just now ISO 26262 being the gold standard that everybody adopts for their internal safety. And now within the next few years, you'll start to see SOTIF become the new functional safety. And then as Tejas also mentioned, SOTIF comes before functional safety if done properly. So then all the cars that you have on the road now that are level 0, 100% compliance with ISO 26262, then you have to kind of go back and rework your process. And then it becomes an ever iterating process that goes on and on. And so it's just a very large time commitment that we don't have the processes in place to expedite in this next year, in the next 6 months, whatever tech gods are out there preaching on Twitter. In conclusion, I would like to thank everybody for tuning in. Hopefully we taught you something, and maybe we won't have you dreaming of autonomous cars quite near in the future as we all were hoping at the beginning of 2020. So just once again, I'm Josh.
I'm Tejas.
I'm James.
Thank you guys.
We do have some questions from the audience. So if you all have a minute, gentlemen, great presentation. But one of our campuseros was asking, do you think that the United States will be the leader and be the first country to come out with most of the self-driving vehicles?
So I personally have been a little bit fortunate to work on these self-driving cars. I've actually worked with 2 specific competitors in the market. I think the United States is definitely pushing this topic, and they're pushing that we get this topic out on the road. But when you look at how driving is just different in all parts of America, right? If you go to Georgia, where I grew up, we have 8 lanes on I-75. If you go to New York City, there may be 4 lanes, but they're actually 5 if you think about how the cars are actually driving. Go to Los Angeles, we have a completely different driving scenario, but then you go to Wyoming, it's completely different. So I don't know who would actually be first, but I think whoever has the most standardized driving patterns, because that's how these vehicles are actually learning. You know, they're making decisions on the different scenarios, they're making decisions on how the environment is, and then they're doing that. I can guarantee that private-owned self-driving cars is probably not going to be prevalent not in America, not in anywhere across the world. And the reason being is the technology and infrastructure. I mean, each of these vehicles at cost runs around $500,000, $600,000. And we're talking if you put, 300,000 miles on them and things of that nature, and then you have to get a new car for another $600,000. And we're past the whole supercar market at that point, right? So I don't think private cars are going to be there. I think the concept of taxiing and robo-taxis, maybe buses with planned routes, that's going to be pretty prevalent. In my personal opinion, since all the testing has been done in America, I think we might be one of the first ones to do it. So for example, I went to Carnegie Mellon, and the route such as going from college to the airport is a pretty standard route. You get on the highway, you take the certain, they drop you off at the terminal station. That might become a pretty prevalent route. And when you call an Uber, it might just be that, okay, it'll be a self-driving car, or instead of a person coming and picking you up. But when it comes to going from like the baseball field to your friend's house, and then going back to campus, I don't think that's going to be coming anytime soon.
Great. Gentlemen, thank you so much for your presentation. It was very, very interesting. And I think our campuseros, not only here in the United States, but around the world, found it very interesting. So I thank you all again on behalf of Campus Party Digital Edition USA. We look forward to next year having you all back with us in person in Detroit. Have a great evening, gentlemen.
Have a good one. Enjoy the rest of the night.
Thank you.
The challenging times faced by business these days have shown the difficulty in managing HR issues and maintaining profitability. Keeping focus on the core business and finding the right partners to help with ancillary functions like HR administration is why more than 500 companies across the country turn to Tryon Solutions. Tryon relieves the stress and burden of HR administration, so companies, small to large, can stay focused on why they went into business in the first place. Small companies turn to Tryon to manage their payroll and taxes, benefits administration, workers' compensation, and regulatory compliance, so they don't need to build a big HR department. Larger companies add Tryon as an extension of their existing HR staffs, achieving efficiencies and enhancing the bottom line. Check out Tryon at RelyOnTryon.com and receive a free consultation from one of its business advisors. It'll be the best business decision you'll ever make.